Hello everybody, my name is Nalic and I am from the Institute of Automotive Engineering of the Technical University Graz. The title of today's presentation is Deterministic Stress Testing Method for Generation of Critical Scenarios. The project was done in cooperation with MAGNA, Steyr, Fahrzeugtechnik, and it's part of my dissertation project. The content contains a short motivation, introduction to a co-simulation framework we developed for this project, another test framework in Vissim, which is used for the deterministic stress testing method. It's called DLL Framework, after which I will introduce the method itself. Here I'll use the shortcut DSTM for deterministic stress testing method, and I'll finish the presentation with the result and summary chapter. First of all, the method we developed is used for testing of automated driving systems. As virtual testing is becoming essential in today's development and testing of automated driving systems, the requirements for the virtual environment are increasing rapidly. First, we need complex and realistic vehicle models. The implementation and adaptation of suitable algorithms should be handled easy. First, the vehicle dynamics should be upgradable and implemented and developed in an easy manner. Second, the implementation and development of a system should be provided, and the implementation and development of sensor models should be provided. Another very important part is, of course, the realistic vehicle environment and the visualization with all objects which it contains. And a very important thing is the realistic and stochastic traffic behavior. To fulfill all these requirements in a certain level, we use IPG CarMaker with the interface to PTV Vissim. IPG CarMaker provides the most of the first points. So actually it provides a multi-body simulation environment with very complex vehicle models, the possibility of implementation of assistance systems, sensor systems, and so on. The PTV Vissim provides a very, very realistic traffic environment with driver models which are based on empiric models of driving behavior, which can be adjusted with a certain level of complexity. So now I'll introduce this co-simulation framework, which is based actually on this interface between PTV Vissim and IPG CarMaker. The co-simulation framework we developed contains a simulation controller, which is shown below, which controls and configures the co-simulation between CarMaker and Vissim. Secondly, the co-simulation itself is running and contains some parts which can be adjusted. In the first part, in the CarMaker part, where we have a multi-body simulation, we can implement the vehicle dynamic, adjust our environment, create our network, and implement our controllers and sensors. And the traffic simulation part, which can be adjusted and controlled by the simulation controller part, contains parameters like input volumes, road entrances, speed distributions, vehicle compositions, and driver model parameters. After each simulation, we record the data and forward the data to the post-processing unit, which analyze and process the data to generate data for scenario generation, to generate data for the assessment after the scenarios are created and detected. So in general, the framework itself is just an easy way to generate synthetic data, which should be used for the scenario analysis and scenario generation part. How this looks like is presented in the next slide. The Co-Simulation Framework is a MATLAB application, and here in the concept part, it's suited in the lower part here, and this is how it looks like. We have a user interface where Vissim and IPG can be adjusted and controlled. This part here is the main part, which contains two different modes, a cluster mode and a manual mode. What this cluster mode exactly is, I'll come in the next slide. Another important part is here the number of kilometers which can be adjusted or which are desired for the testing procedure. We can adjust here any number of kilometers, and the co-simulation will continue until it reaches this number of kilometers. The second part is the cluster mode, as I said, and it can be activated here, but as said before, I'll explain it later. In the manual mode, if we don't choose the cluster mode, we are able to adjust the vehicle compositions, the vehicle types, and the vehicle volumes without using Vissim. We can all handle here in this user interface. This gives the user the possibility to just use this part here for the co-simulation procedure. So I'll continue now to the cluster mode. During our project, we collected traffic data from the Alplab test road in Austria. This is the official test road for testing automated driving systems. It's close to Graz, where we took one section of this Alplab road, the A2 section from Graz west to Lasnitzhöhe. And this section here was equipped with a lot of measurement equipment to collect data for the traffic model. We had 21 counterpoints, and we measured in the time from between 1st of October 2017 until the 31st of March 2018. Using the data we collected, we calibrated the vehicle inputs, the vehicle compositions, driver models, speed distributions, and used it for the model we implemented in the co-simulation. So the second framework we developed is the DLL framework for the DSTM. This framework is created to increase the number of safety relevant scenarios which can be detected in the co-simulation procedure. The reason why we need it is that because the safety relevant scenarios are rarely occurring in the IPG Vissim co-simulation. The solution was to manipulate traffic participants in the surrounding area of the ego vehicle. This is done by using an external driver model DLL interface provided by PTV Vissim, which is provided as a C++ code. With this code, the participants can be manipulated. ADAS functionalities can be implemented for each traffic participants, test cases for different applications like platooning, column stability, and so on. For what we are using it, of course, is manipulation of traffic participants in the surrounding area of the ego vehicle. The class diagram of the framework is presented here. The left part is the part which is provided by PTV Vissim, and the right part is the part we developed in our project. The ego vehicle class, the nearby vehicle class are very important. They give us data for the ego vehicle and the nearby vehicle. The data can be read and set during the simulation. The DSTM is implemented in the injector class, where the manipulation process is defined. So the next part is about the deterministic stress testing method. Coming to the DSTM, I'll introduce the background for the method. For the DSTM itself, we only considered highways because of the moment. At the moment, we are focusing on the test of a highway chauffeur. Based on a database provided by Statistik Austria, we got all accidents from the year 2009 to 2018. In this figure, The blue bars represent accidents with one part involved, and the red bars, the accidents with more than one part involved in an accident. We found 9 dominant accident types where each accident type has subtypes. For the DSTM, we found 2 major types to be relevant and interesting. We divided them in the longitudinal scenarios and lateral scenarios. First, I'll start with the longitudinal scenarios. These scenarios here, they contain accidents with stationary vehicles and accidents with moving vehicle with speed reduction. These are shown here in the right figure. The lateral scenarios are the second type of scenarios which are dominant, and they occur while a lane change was performed. So we will start with longitudinal scenarios of the DSTM method. In this figure, we can see the relevant situations for the DSTM. One ego vehicle with 2 traffic vehicles. Each is in a certain TVC column. TVC means traffic vehicle column, and a certain lane. TVC columns are defined by a certain distance range from the ego vehicle. In the DSTM, these vehicles are manipulated to brake in a defined manner. They can reduce the speed, or they can make a fully braking maneuver. To trigger such an event, we have to calculate the event matrix and are looking for relevant combinations. Here are 2 event matrices for 2 lanes and 3 lanes. First, I'll explain the calculation of the event matrix. Here an example, 5 cars on 3 lanes in different TVCs with fixed distances. If something like this occurs, the distances of the traffic vehicles are checked if they are TVC column range. The traffic matrix is calculated as follows. Each position where a traffic vehicle is available, a true value should be set. So we check if the distances are in a certain TVC column, and if they are, we set a 1 for each traffic vehicle. In this part here, it looks like this. Now we go to the trigger of the braking maneuver. We have to check which combinations are relevant. Here the combination matrix which is compared with the event matrix and the combination matrix table. This table here represents the relevant traffic maneuvers which should be triggered. Again, the example as before, we have here now 4 distances and these traffic vehicles and the traffic event matrix as calculated before. And the combination matrix, which is similar to this one, is the combination matrix CQL3. In this combination, we can see these 2 parts here are relevant. Only if a vehicle is in front of my vehicle, doesn't matter in which traffic vehicle column it is relevant. It is a relevant combination. Now we can have here a 1 or 1 in the middle part, or a 1 in the upper part here. So in this case here, these 2 cars in the vehicle column 2, T12 and T22 will start braking. How this looks like in a traffic simulation is presented here. Here the white part represents the ego vehicle. So if an event occurs, or if a combination occurs, these relevant combinations are yellow. And one braking maneuver is triggered. And this braking maneuver here is just a reduction of speed of the vehicle in front. What the ego vehicle is doing here is changing the lane to avoid a collision. So in the next part, while the simulation is moving and going on, this event matrix is calculating continuously. And now the event matrix or the DSTM found another combination, and this is this one here, where we see these two yellow cars. Now the car here in front will start braking, and this car will not brake. Now we see a reduction of speed of this car here and a reduction of speed of the ego vehicle. So after each event, the cars are again red and they follow the Vissim traffic behavior. How this looks like in the co-simulation, it's showed here. In this movie here, we have a collision with a track here which starts braking. And we can see here that the car starts braking, but the ADAS function, or the automated driving system, which is implemented in this car here, is not changing the lane and is not able to avoid a collision. In the next simulation, we have a reduction of speed of the car in front. And the ACC handles this situation well enough. So now I will move to the vertical scenarios. The vertical scenarios are much more easier because here we only consider the lane change or the cut in from left and right. So if the ego vehicle is in this lane here, the relevant lane changes from left to right are the traffic vehicles which are passing the ego vehicle. And they can start the lane change in 3 initial points or initial times in this part here. So they can start changing the lane here, here, or here. How this is triggered is stochastically. So we never know if it will start here, here, or here. And the same is for the lane change from right to left. Here a short video for this. Here we have the car, which is relevant, and it starts at the first point to make a lane change. So here we see the car, the ego vehicle is following the truck, and it's driving 92 kilometers per hour, and after the lane change, it reduces the speed. This is considered, in our case, to be a relevant scenario for testing of an ADAS system. In this case here, for example, an ACC. Here we have another example. But here at the second point, the lane change starts and the speed reduction is performed. So if we summarize the results, we performed a simulation of 1,000 test kilometers with and without DSTM, and we evaluated collisions, cut-ins, and near collisions. Here in these tables, the results are summarized. In the simulation of 1,000 kilometers without DSTM, we detected no collisions, 68 near collisions, and 167 cut-ins. And using the DSTM, we generated much more scenarios. In the DSTM simulation of 1,000 kilometers, we detected or generated 47 collisions, generated 289 near collisions, and we generated 723 cut-ins. To summarize all, the number of detected scenarios has been increased using the DSTM in combination with the IPG car maker and PTV Vissim interface. With additional metrics, there is a possibility, of course, to generate more and detect more scenarios. The provocation of critical maneuvers and scenarios has shown that this environment or this co-simulation can be adjusted with a more dynamic traffic environment around the ego vehicle. Additional, for what the DSTM can be used is some other test processes which I mentioned before, and this is, for example, for testing platooning and testing column stability and maybe some other applications. Why it's possible? Because using this DLL framework, we can actually easily adjust the surrounding as we wish. It doesn't have to be, like in our case, just to consider longitudinal lateral scenarios or special longitudinal lateral scenarios we took here. It can be used for also the urban environment. We can adjust pedestrians in an urban environment, manipulate them in a defined manner. Some of the work I presented is published in some conference papers, and 2 papers are in preparation. One journal paper will describe in more detail the stress testing method itself, and another paper describes and provides the code for the manipulation process. Thank you for your attention.